Right. So as I was saying, we'll be looking at runtime analysis, and what we'll find is that most of our functions will fall into 7 different functions. You have, of course, come across these before, but we're just going to remind ourselves what these functions are and how they compare. The first is the constant function. So if we have a function f of n that is equal to c, we'll see that n doesn't actually come up in the expression of our function, which means that regardless of the value of n, the value of a function will remain c. Right, so its value is constant. It doesn't actually depend on n. We have the logarithmic function, which we've kind of discussed a little bit before. It comes up a lot in computer science because oftentimes we use a divide and conquer strategy, which means that we're splitting the work over and over again until we get to some base case or some simpler case that we wish to deal with. And so because the log function log b of n asks us how many times can we divide n by b, it comes up a lot. Right? And if we find that the log base b of n is x, that's equivalent to saying that b raised to the power x is equal to n. Then a linear function, this is probably the first function that you guys learned, I don't know, way back in grade 8. So here we have that for various inputs of n, we have n multiplied by some constant multiplier, some coefficient, plus sometimes some constant. Yeah, I'm sure you remember that expression, y equals mx plus c. But the idea is that the rate of growth of the function is actually proportional to our inputs. And that's a linear function. Then we have a function that's a combination of linear and logarithmic. That's n log n. We'll find that that grows at a faster rate than the linear function, because certainly for values greater than our base, log of n, for n is greater than the base, will be greater than 1. So n log n for values larger than the base will be greater than a linear function, however, it'll be less than a quadratic function. Then we have our quadratic function. So we take our inputs and we square them, and some constant multiplier of that is the function that we get. So our function is proportional to the square of its inputs. Then the cubic, so our function is proportional to the cube of our inputs. Each of these has a higher and higher growth rate as we get to larger and larger powers of our base. And the exponential, which is the one that has the largest growth rate of the functions that we look at. Here we have some constant base, and based on our inputs, we are raising that base to the power of our input. The greater the input, the much greater the value of our function. And this grows at such a rate that it really isn't practical to have algorithms that run in exponential time, because what we'll see is that the amount of time that it takes to execute these functions grows rapidly as a factor of our inputs. And so it isn't exactly practical to have functions such as these. So if we're comparing 2 different algorithms that do the same thing or achieve the same goal, then we would not choose the one that has that runs in exponential time. All right, so this is a log-log chart. So it's simply a chart that does not have constant differences between the points in our charts. It allows us to be able to look at functions at a much larger scale. And what we see is that linear, which is represented by the green line at the bottom there, has a much slower growth rate than a quadratic and less than a cubic. So if we have 3 different functions and we found that the runtimes of each are linear, quadratic, and cubic, we would definitely choose the linear because that grows at a slower rate. All right, we already have some questions. All right, as usual, there's one about the prac W linked list. Why are we doing these calculations? So what is our objective? All right, so as I said, we would like to be able to analyze our algorithms to be able to tell how their runtime grows as a function of their inputs. So oftentimes, most often, we'll find that our functions, because they are working on data, that their runtime depends on the amount of data we're giving them, but also sometimes certain attributes of that. If we look at different sorting algorithms, if your input is already sorted or mostly sorted, then oftentimes they'll make it run quicker. Although other times that can be the opposite. And so, but often it depends on the size of the input that we're giving it. And generally, the larger the input, the longer it takes to run the algorithm. So we would like to be able to compare different algorithms, to be able to understand how their runtimes grow and to be able to compare them, to be able to choose which is the most efficient. And so to be able to do that, we first look at these different functions, then we'll see how we can go from given some kind of pseudocode to actually finding out how the runtime of such a function would grow as a function of its input. All right, so that's where we're going to. Should we be able to draw a graph like this? No, you don't have to be able to draw a log-log chart. I will tell you exactly what it is that you have to understand and be able to do. Is there some sort of Eclipse plugin that computes the running complexity of a Java method? No, not that I know of. There certainly are, and you wouldn't even need a plugin for this, but we can time our algorithms by implementing them and simply calling time before and after we run our method. And that is a way that we can analyze our methods, but we'll see that there are some advantages and disadvantages of that. All right, and that forms part of our discussion. So here we have the graphs of the 7 functions that we discussed. The constant one, that'll be the first one here, g of n equals 1. So this for any constant value c, in this case we look at 1, the graph of our function would look like a horizontal line such as this. As in, regardless of the value of x, y will be the exact same. So it's a constant function. The next one is our logarithmic. We see that that grows at a fast rate for small values. Those are values less than the base b. But as soon as we pass that, the growth rate slows to a considerable degree. Right? And its slope there is actually less than that of a linear function. Then we have the third one at the top on the right, g of n equals n. That's a linear function. That should be very familiar to us, a straight line. So our outputs are proportional to our input. Then we have g of n equal to n log n. So this is the combination of linear and logarithmic. So it grows at a faster rate than each of those, but at a slower rate than the quadratic function, which we have in the bottom left there, g of n equals n squared. That's a parabola. We should be comfortable with that. We should have seen that a lot in high school. Its growth is greater than that of a linear function, but less than that of a quadratic function, which we have the next one there, g of n equals n cubed. That has an even faster rate of growth. But one which is much faster than all the rest is our exponential. You'll see for small values, it's rather small, but as soon as it gets larger values, it starts to grow at a very fast rate and almost goes straight up as a vertical line. It grows at a very quick rate. For log, where do we get the base from? Well, in computer science, if there isn't a base given there, then the assumed base is 2. Right? If we're in mathematics, the assumed base would be base 10. So oftentimes we'll be looking at log base 2, or sometimes natural logarithms, which is log base e. All right, but if there isn't a base there, then the assumed base is 2. If it's different, then that will be explicitly given 2. All right, so we remember that data structure is simply a way of storing and manipulating data. We already talked about the fact that if we abstract that, it really is simply how can we manipulate that data, and we use interfaces to deal with that. If we're talking about a concrete data structure, then we have a way of storing a particular type of data, and then ways of accessing and manipulating that data. Then an algorithm, as you learned from first year, is a recipe. It's a step-by-step process of solving some problem. It should, of course, be done in a finite amount of time, or else it isn't practical. And so these attributes of our algorithm will impact the runtime. Right? What type of data structure we're working with, how it's organized, the size of the data that we're working with, and of course the algorithm itself. Those will all impact the runtime of our particular method. All right, there's another question, but the answer of that will come in the next couple of slides. So most of the algorithms that we deal with actually do some work on objects that are passed to it, and then output some other object once that work has been done. So transform the input object into an output object, and the runtime of it generally grows as a function of that input size. So the larger the input, the longer it takes for us to be able to transform that to some output. It's difficult to actually calculate the average time. So if we want to consider, well, how does our algorithm run for any given input? And to figure out, well, of all those inputs, what is the average time that it takes for our algorithm to run? It is a useful metric, but it's very difficult often for us to be able to determine that. So we have the choice of, we could look at, well, what's the very best time that we could get, or what's the very worst time that we could get? And you could say there are arguments for both. You want to know, well, in the best case, what's the quickest that this algorithm can run? But because you want to be able to run your algorithm for any input, it's more useful, I would argue, to be able to consider the worst time and know that regardless of the input that's given, at worst, it'll take this long. Right, and so that's why we focus on this worst running case. It's easier to analyze, certainly, and it's crucial in a lot of different applications because you don't want there to ever be a case where, oh, well, for some inputs which we haven't considered, it may take a very long time. But on average, this is how long it takes, and the best case is how long it takes. You should actually be accounting for all of them, including the worst case, that regardless of inputs, you know that the bounded time for this will be such. All right, and here we have graphs for different inputs, and we're calculating 3 different times, the best case, average case, and the worst case. So for different input sizes, 1,000, 2,000, 3,000, 4,000, these are the different running times that we could be considering. All right, the worst case will be the longest amount of time. So if we're looking at those sorting algorithms, perhaps this is one where when our input is completely unsorted, it'll take the longest number of operations. And so here we would be considering that particular worst case. All right, because certainly that's more useful. If you want to know that, well, this algorithm that we're using to sort may take a couple of seconds to run or a couple of hours in the worst case, then you should be prepared for it to be able to run that couple of hours. And that allows us to compare different methods, look at their worst cases, and say, well, the one that has the quickest worst case would certainly be the optimal one, even if perhaps its average or best case is greater than some of the others. Right. So how could we actually do this? How could we actually be able to compare different algorithms to be able to tell which is better? One method of doing this is actually implementing those algorithms, running them for different inputs, timing that, and graphing it. So we could write the program, actually fully implement it, run that program for varying sizes of inputs, and then use a method like this Java one that takes an accurate measure of time. We could do that before and after our function. We subtract one from the other. That gives us the length of time that has elapsed while that function has been running. Then we could plot those results for our various inputs, and that would show us how this particular method performs for different inputs. Right, and this is an example of that. So here we run this algorithm which computes the multiplication of 2 matrices, 100 by 100 matrices. We run a different software and hardware platforms. So here we have for each of these software platforms, the Java Virtual Machine, Oracle JVM, and on different hardware. So we have the in purple Dell machine, right up to a Raspberry Pi there in red and blue. We see that the runtime differs based on the software platform they're running it on. The low-level ones will run a lot quicker than something like Java VM, the Jam VM. And for our faster machines like the Dell, it'll run a lot quicker than something like a Raspberry Pi, right, which is usually used for embedded systems. And so, great, it does tell us something about how long this method would take to execute, but we understand that it's also a function. It also depends on the software and hardware platform that we're running this on. So it is useful. However, it's limited because for us to be able to compare any two algorithms, we'd have to be running them on the same machine with the same software environment, or else those would affect our results. So if we knew all the algorithms we wanted to consider and we had the exact same setup, then yes, we could do this. But as soon as we want to be able to compare it to something else on a different setup, it's very difficult for us to do that. So there are some limitations to this approach. Firstly, you actually have to go and implement that function. You have to run it several times with different inputs. However, if we want to compare two different algorithms, then we have to make sure that they're done on the same hardware and software environments, or else the results can't be compared head to head. And of course, it's different, or rather, it's impossible for us to be able to run this on all possible inputs because that would take infinitely long. And so we'll usually simply take some representative set. But what if that doesn't include some very important possibilities? They would lose out on that. Okay, this question of the pracs, please go and watch the recording that's been asked and answered. And so another more useful way for us to analyze this is by counting primitive operations. All right, we have a question that actually had to do with what we're discussing. Why do different software environments have different runtimes for the same algorithms? Okay. I'm quite sure last year you talked about different types of high-level languages, right? That these can be compiled or interpreted. That something like Java actually has an intermediate language that our code is changed into that can then be executed on a Java virtual machine. So basically, it depends on how that software that you are executing your code on actually takes that code, changes it into machine instructions, and executes it on that platform. Right? So based on those differences, it would take a different amount of time to execute instructions from on different software environments. Right? Even if we're talking about, yes, low level is usually better, less is done to execute that instruction. So if we're talking about Java, then that's even more so because Java creates this creates the same platform on top of different hardware platforms. The fact that I can take my code and execute it on a Mac machine or a PC or even like a Raspberry Pi, I can do that because for different architectures, different Java virtual machines have been implemented. And so you can take this code and it's portable. Anyway, anything that has the Java runtime environment, you can execute this code on it. But different things are actually happening when you execute that code. There was the question of whether references in Java are actually pointers. And what I said is that it really depends on which hardware that code is eventually executed on, because depending on the implementation, it does different things. Right? And because of that, it'll take a different amount of time to execute based on the hardware, but also how that software interacts with it. So the compiler of each language play a part, yes, but also depends on whether that language is actually compiled or interpreted. Right? But certainly lower level ones like C would execute quicker than something like Java or C++. Yes, it does depend heavily on hardware, but it depends on that combination of hardware and software. You could have the exact same machine, but you guys are running different operating systems or different execution environments, different languages, and you execute very similar code, and it would take a different amount of time. This is why for languages such as Python, if they want to create libraries that run very quickly, they'll actually write those in C because those run a lot quicker, and then simply build a wrapper, a Python wrapper, that allows you to call that code within Python code. All right, so a lot of those libraries aren't actually written in Python, even though you can use them in Python because it doesn't execute as quickly as a lower level language like C. Why use Python in the first place? Well, because it has a lot of useful libraries. Um, it has been designed to be really simple. You can get going with just a few lines of code. And so it brings together the best aspects of various languages to create a very useful, simple language. Right, and that's shown by the fact that it has now been accepted in a lot of different spaces: web development, regular application development, working with macros in Office and such. Right, so now we want to find out, well, is it actually important for us to find out what that exact runtime is when we realize that that runtime isn't absolute? It depends on the hardware and software environment that you're executing this program on. So it doesn't tell you something universal about that code. It simply tells you running on this machine with this software environment, it takes this amount of time. So great, if I'm executing two algorithms in the same environment, then I can compare them head to head. However, that runtime is not some intrinsic attribute of that method. It's, yes, the method itself, but then also that environment. So is there a way for us to evaluate this algorithm separate from that environment? That would be more useful to us. All right. And so instead of actually implementing this algorithm, we can instead look at a high-level description of it, like pseudocode, then characterize the runtime as a function of the input. So see, what does this algorithm actually do on that input? Based on that, try to characterize the function's runtime as a function of that input. Because we're expressing it as a function of the input, as in of some function of n, then we're taking into account all possible values of n. We don't have to try and do as many examples as we can, knowing that we're always going to leave some out. Instead, now we can express it as a function of that n. And as we said was our objective, we now can evaluate its speed independently from that hardware and software environment. And so this is a lot more useful to us. Now we can compare any methods regardless of where they'll actually be executed, and we can get some notion of what their runtime would be. So what do? We count primitive operations. What are those? Well, they're the basic computations that are performed by an algorithm. We can identify them in any high-level representation like pseudocode. We don't actually have to implement these. They're largely independent of programming language. Certainly, if I give you pseudocode, you could go and create VB code that does what that pseudocode expresses, or you can create Java code that does that same thing. All right, so it's independent of the programming language that you're using. Its exact definition isn't important, simply what you're trying to achieve there, what you're describing. And we can assume that we assume that each of these primitive operations take a constant amount of time. We'll see in the next couple of slides why this is okay, why we can assume that, even though knowing that the circuitry for addition and subtraction and multiplication is actually different. And so they would take a different amount of time. We can assume that they're the same because we'll see that there's a constant difference between them. All right, but we're getting to that. So what are primitive operations? We have to agree on what these are. Right? This may be slightly different from what you've done in second year or first year. So please, once we've agreed on this, this is what you must use going forward. And so we will right now, we will say that evaluating expression will be a single primitive operation. Although, let me write this down. If we have something like this, a plus b over 2, we will understand that there are two operations being evaluated here. So we'll say that this is a single primitive operation. And once that has been evaluated to some value and divided by 2, that is another primitive operation. Right? So evaluating expression, although we understand that the way that this is done in our machine, we already talked about that operator precedence. So each time those things are evaluated, it's replaced by the value that has been evaluated, and then the next operation in that precedence is executed. All right, so that one has a caveat. If it's a complex expression, then that can take more than one operation. All right, but evaluating each of those sub-expressions, each atomic expression, that takes a single primitive operation. Then assigning a value to a variable. So if in our pseudocode we have some variable and we're assigning to that some value, we will say that that is a single primitive operation. If we're indexing into an array, so anywhere we have some array and we are indexing into that array, then that will be a single primitive operation. Calling a method, that'll be a single primitive operation, and returning a method. Right, so when looking at our code, we'll look at each of these things as a single primitive operation. That now allows us to be able to count up the primitive operations within any method. All right, so we want to do exactly that for our first example. We have here an algorithm that wants to find the maximum value within the first n values within an array. How do we do that? You should remember this from first year. We assume some initial maximum, then we iterate through the entire array, each time checking is the current value greater than our maximum. If it is, then we will update our current max. Now, there's some decisions that we're making throughout here. Right? So for example, let me get something that will probably be asked. For this conditional statement, we understand that each time we are every time we reach this conditional statement, we are evaluating the condition, right, to see if it's true or not. However, we will only execute it if that condition is true. So we are going to evaluate AI greater than current max. However, current max being assigned the value AI, that won't happen every single time. However, we're going to assume worst case, which means that if this array was sorted in ascending order, then every single time we compare the current to our current max, then it would be greater. AI would be greater than that current max, and so we'd update it. So we're going to count it every single time. All right. So let's try and count it primitive operation. For line 2, right, the very first statement within our method, we're doing two things. We are indexing into an array, A0, and we're assigning that value to the variable current max. So there are two primitive operations. If current max is also declared there, then there would be 3. Why would there be 3? Because we agreed that when you create an actual variable, Java gives it some initial value. And so there is an implicit or rather an unseen assignment that happens there. But here it's already been created somewhere else. We're simply assigning it the value A0. So there are two operations, indexing into an array and assigning a value. Then the header of our for loop. Well, there are two groups of statements that are executed here. Some that are executed only once, and then others that are executed each time that we execute our loop. I'll quickly underline those that are only executed once. Declaring the variable int I and assigning it the value 1, that is only done once. If that was done every single time we execute our loop, then the value would remain 1 throughout the execution of the loop. Right? That wouldn't be very useful. However, those two statements are only done once. There is the assignment statement that I is given the value 1, but that declaration statement initially gives it a value of whatever the default value for an int is, which is 0. So on the right there, you will see that 2 for line 3. That's where that comes from. And that is only done once. So that isn't multiplied by the number of times that our loop is executed. Then for the rest, rather than jump to exactly how many times they're executed, it's more useful to simply count up the number of primitive operations and multiply that by some number that we will later decide what that is. All right, so while the answer is already there, what you usually do is for each line say, I'm executing some number X of primitive operations, and I am executing that some number of times big N. Then once we've finished counting up all the primitive operations, we'll go and look at, well, what is that big N? All right, because the answer is already there, let's just decide how we got to that. We're going from 1 up to, but excluding N, and that's N minus 1 different values for I. Right? It doesn't include 0 and it doesn't include N, so it's from 1 up to N minus 1. And that's how we get that n minus 1 that's being multiplied by all the primitive operations within our loop. So where do we get the 3 from that we are multiplying by n minus 1? Well, there is a comparison here, I being compared to n. That will be one primitive operation. Then we have I plus plus, right? I plus plus is equivalent to I is assigned the value I plus 1. So to be consistent, to make sure that for equivalent statements, we have the same number of primitive operations, we'll count up these ones over here, and that is evaluating expression, which is 1, and assigning a value to a variable, which is another 1. So this is 2 primitive operations. So those 2 primitive operations plus that single comparison, that is done every single time that our loop is executed, because, well, the one is to make sure that we still should be executing the loop, so is I still less than n, and the other one, we increment the value of I each time that we execute the loop. All right. Even though that may well be done at the end of the loop, that is done every single time that loop is executed. So we have 3 primitive operations that are done as part of our loop header. Then within the loop itself, our if statement is executed each time, and it has, well, we're indexing into an array, so that's a single statement or a single primitive operation. Then we're evaluating an expression. We're evaluating is AI greater than current max, and that's another single primitive operation. So those are 2 over here in the 4th line. All right, I see if there are some questions, I will get to that. Then current max being assigned the value AI. Yes, we know it may not happen each time, but we're going to assume the worst case, so it's done every single time. AI is indexed into an array. That's a single primitive operation. Then the assignment statement there, assigning that value to the variable current max, that's another one. That gives us the 2 in line 5. Then returning, so return current max. We said returning from a method is a single primitive operation. So that gives us that 1. If we're instead returning something like current max plus 2, then that will be 2. Evaluating what current max plus 2 is would be a single one, and then returning would be another one. All right, but here we're simply returning a single value. All right, so we have some questions before that. Can I explain the loop header one more time? All right, I'll do that. Going back to incrementing, does this mean plus plus I is equivalent to 1 plus I? Yes. All right. So incrementing, whether it's incrementing before evaluating or incrementing after evaluating, we'll take both of those as 2 primitive operations. Right. Let me just erase all this since we want to go back. So the question was, can I explain the loop header one more time? Yes. We understand that this loop header has 2 groups of operations. One group that is executed only once, and then another set of operations that are executed every time the loop is executed. So we'll end up with, well, some number of operations, let's call that X, is done only once. And then some number of operations, we'll call that Y, is done big N number of times, is done every time the loop is executed. So that is done the number of iterations of our loop times those number of primitive operations. So which one's only done once? Int I being assigned the value 1, that is done only once. When we have a declaration like int I, right, for a primitive type, then that's given the value. It's actually created, so it's dynamically assigned some space in memory and given the value 0 initially. So that's a single primitive operation. If it were a reference type, we're given the value null, that would still be a primitive operation. Then it's assigned the value of 1, that's another one. So we have that our X is equal to 2. Right? 2 primitive operations are executed just once. Then there are ones that are executed every time the loop is executed. We have evaluating the expression I less than n. There are simply values on the left and right side. If we were evaluating some statement there, like let's say it was n plus 1 or n minus 1, that would be one primitive operation. Then evaluating that Boolean would be another one. But here we have just a single one, is I less than n. So that gives us, let me put this in parentheses, 1 there. Then we just agreed that I plus plus is 2, 1 plus 2, and that's multiplied big N times. Right, so that's what we have. Then we would consider, well, what is big N? How many times is the loop executed? Well, it's from 1, then 2, then 3. These are the values of I each time, up to N minus 1. And those are N minus 1 values. So they are N minus 1 iterations. So this is multiplied by N minus 1. Right, and that's how we get this 2 plus 3N minus 1 that we have for line 3. Okay, and because that N minus 1 is the number of times the loop is executed, everything within the loop and this part of the loop header will always be executed N minus 1 times. Yes, we realize that for conditional statements that may not be true, but we will assume the worst case. And in fact, we'll go further than that. We'll see that when we have an if or an else, if and an else, even though only one of those will be executed, we'll simply count all of them up. Right? So that is a simplification on our part. Great. Now what do? We add up all these primitive operations. You'll see that for each one, we have evaluated what that statement is actually equates to. Then we count up all our n's. We get 7n. Then we count up all our constants. So we have here minus 5 plus 2 plus 1. That gives us minus 2. All right. So we have some expression of the runtime of our function as a function, or the runtime of our algorithm as a function of the input size. So based on the number of elements in A that we're actually counting up, based on the size of our array, this is how long this method will take. 7n minus 2 primitive operations. Now, note, that isn't actually a time, right? That is simply how many primitive operations will have to be executed for this algorithm to complete its execution, in the worst case. But what does that actually tell us about the amount of time that it will take? That's what we want to now resolve. There's a question. One is for the Boolean operation. Yes, that Boolean operation, we are evaluating an expression. I less than 1 is an expression that is a single primitive operation, right? And it's a basic, it's an atomic expression. It's a single one. So we said that it executes 7n minus 2 primitive operations in the worst case. Then we realize, depending on how long each primitive operation takes, that will tell us how long this it'll take for this algorithm to be executed. So Tn is the time that will be taken by this method in the worst case, Tn. And we realize that if all of these operations take a certain amount of time, then Tn will be somewhere between the number of operations multiplied by the quickest time and the number of operations multiplied by the worst time. So the operation that takes the longest amount of time. It'll be somewhere between these two things. Right? Someone asks, why was the total 7n minus 2 and not 7n minus 4? Right? Where do we get minus 4 here? Where do you get minus 5? All right, I understand that you have that there's minus 5 here, right? But remember that there's a 2 over here and a 1 over here. Okay, and we shouldn't really be wasting time on arithmetic. That is for you to learn somewhere else. So here we have, why is this true? Why is it between some multiple of 7n minus 2 and some other multiple? Well, let's say each of you is a primitive operation, right? And we're going to take some work that has to be done and divide it up amongst all of you. So the amount of time that we spend doing this work, if the slowest amongst you to do all the work would be the amount of time that they take to do a single operation multiplied by all the operations that have to be done. Then if we happen to give it to the person who is quickest, it would again be the amount of time that they take to do a single bit of work multiplied by the number of operations that have to be done. Right? And of course, if we divide it amongst all of you, because each of you is a different type of operation, then it would be something between those two numbers. Right? It would be something between getting the fastest person to do it, to do all the work, and getting the slowest person to do all the work. Right? Though granted, we're counting up the amount of time spent doing work, not the amount of time that all of you take to do it. So we're counting up the amount of time that each person spends and summing those up. So it's the same here. If we consider them all to be the same as the fastest operation, we get this smallest bound, right? If we multiply all the operations by the slowest one, we get this upper bound, and the amount of time that it takes for this worst case is between those two. And so we can say that Tn is bounded by two linear functions. It lies somewhere between these two linear functions. So if we're to draw what these two linear functions look like, let's say we actually had those values of A and B, and then we can actually look up what the time taken to execute operations are on our machine, and we could actually do that for a processor. We can look up what operations it supports and how long those take, but good luck finding those manuals. And perhaps we find that it's two linear functions that look like this. We know that our execution time is somewhere between those, right? It lies somewhere between those two linear functions. It's bounded from below by this A7n minus 2 and bounded from above by B7n minus 2. Right, and that is useful. That tells us something about its behavior, how its runtime grows as a function of its input. What would happen if A is equal to B? Well, is that possible? Can every operation on a machine take the exact same amount of time? Remember that although we abstract away and we simply think of instructions that we write into a method, that there actually is circuitry that is comparing numbers, adding one number to another. Something like multiplication is addition over and over and over. It can't take the same amount of time as addition, right? These things won't actually take the same amount of time. But we are now abstracting away from that. So we're going to drop A and B and simply say that it's between those things. Okay, so some of you have done numerical analysis. You have looked at things like Cauchy's theorem and Squeeze theorem. Great, you understand that you can then find the limit between those two functions. We're not concerned about that here. All right, when testing algorithm A and B, is it possible that the algorithm A will run faster than algorithm B on one machine, and algorithm B will run faster than algorithm A on a different machine? Well, if it's just different machines with the same software environment, then that is unlikely. But if you're talking about different languages and different machines, then yes, that could be possible. That could be entirely possible. All right, so here we want to look at a different example. Again, we have some simple assignment statements in lines 2 and 3. So those simply get a single primitive operation. Then we have our while loop condition is less than high. And so because that's executed every time that our loop is executed, this is a single primitive operation multiplied by the number of times that our loop is executed. And we do the exact same thing for all the other statements. We have here low plus high, that is evaluated. Then that's divided by 2, that's evaluated, that's 2 operations. And that is assigned to the variable mid. So it's 3 operations executed n times. Our conditional statement, the condition itself is a mid less than x, indexing into an array, that's a single operation, evaluating expression, that's another operation. We have there 2 multiplied big N. Assigning the value mid plus 1 to low, mid plus 1 is a single operation, assigning it to low is another operation. Then the else condition, is a mid equal to x? Indexing into a mid, and then evaluating that expression, that is again two statements or two primitive operations. Return mid, that's a single primitive operation. Then mid minus 1, evaluating that, assigning it to high, that is two primitive operations. And return fail, that's a single primitive operation and it's outside our loop, so we don't multiply that by the number of times the loop is executed. So this is what you'd have. Then you go and consider, well, let me actually write these down as well. All right, what is big N? What we're doing here is a binary search. So each time we have, initially we have a sorted array. We want to find an item within that array. We check, is it in the middle of my array? If it isn't, then we consider, is what is actually stored there less than or equal to what I'm looking for? And then we figure which half of the array we should look in. If what I'm looking for is less than what's in the middle, I look at the left half. If I'm looking for is greater than what's in the middle, I look at the right half. I do this how many times? Well, I do this as many times. In the worst case, if the thing isn't actually my list or it happens to be at some value that I can only find after halving my array over and over and over until I get to a single element. The greatest number of times I can do this is log base 2 of n being the size of the array. All right, so I can only break my array into two, halve it over and over and over, log base 2 times. So if this array was of length n, small n, then all of these big N's become log n. All right. If we're to express it in terms of the parameters that were passed there, the arguments that were passed there, then n is just taken to be h minus l. Okay, so some number of indices that we're searching over. All right. Should we come to the idea of a binary search? We understand that in the worst case, it's executed log base n times, n being the size of the array that we are searching, and we multiply that by all the statements that are within our loop. The other statements aren't multiplied because they're executed only once. We add those all up, and we end up with 12 log n plus 4. And so we understand that this does not mean it will take 12 log n plus 4 seconds, but it is somewhere between 12 log n plus 4 multiplied by the time it takes for the quickest primitive operation to be executed, and 12 log n plus 4 multiplied by the slowest primitive operation. So it's somewhere between those two times. So what does changing the hardware and software environment actually do? What we realize is that because the primitive operations take a different amount of time on different combinations of hardware and software, it actually affects Tn by a constant factor. It doesn't change the number of primitive operations. It simply takes the time that each primitive operation takes. So our fastest one may be faster or slower on a different hardware and software combination environment, and our slowest one may be faster or slower on a different environment. However, they will all be faster or all be slower. All right? It'll be changed by a constant factor. It won't actually change the number of primitive operations. So something that has a linear growth rate on one software and hardware environment will still have a linear growth rate on another software and hardware environment, as in it will still depend on its input in the same way. If you're doing a linear search through an array, then the number of operations to execute will still be some linear function of the size of the array. As the array grows, the number of operations that you're executing and the time that it will take will still depend on that size in some kind of linear fashion. As in, when the size of the array doubles, the time taken will double. If the size of the array triples, the time taken will triple. That will not change. It is an intrinsic property of that algorithm. Right? And that should explain to us why this is important, why this allows us to be able to compare two different algorithms. Yes, it'll take different amounts of time to execute on different hardware and software environments, but our understanding of how the amount of time it takes to execute depends on the size of the input is true regardless of where we execute it. That's why that's important to us. All right. And why does knowing the growth rate matter? Why do we care about this? How does it help us to compare different functions? Well, based on the growth rate, that function, the amount of time that it takes changes very differently. If we look at a logarithmic function, so in our second column there, the first one, the actual values of functions, for different values of n, log n is equal to what's given there. So for n equal to 8, log n is 3, because I can divide 8 3 times by 2 before I end up with something 1 or less. Then for an n of 512, log n is equal to 9. So what does that tell us? That tells us that for that algorithm binary search that we had, that if the array was of length 8, then I would do some multiple of 3 operations, right? For a size of 512, it'll be again that constant multiple of 9 operations. It wouldn't grow that much, right? It would simply take 3 times as long on an array of 512 elements compared to an array of 8 elements. However, if I was doing a linear search instead of a binary search, then it wouldn't take 3 times as long. It would take how many times as long? It would take 512 divided by 8, significantly more time. All right, that tells me something about that algorithm. Then if it was an n log n one, for 8 inputs, it will be some multiple of that 24 operations. For 512 operations, I'm now in a much higher band. I'm looking at thousands of operations. For n squared, for my smallest input, I'm looking at tens of operations. For my largest inputs, I'm looking at hundreds of thousands of operations. So if you had 2 functions, one that runs in logarithmic time and one that runs in quadratic time, then you would obviously choose the one that runs in logarithmic time because it would run a lot quicker than the one that runs in quadratic time. Right. We see that for cubic n cubed, it is even worse, right? For something in the order of hundreds of inputs, we end up with something that's in the millions here. Right, so it grows even quicker. Then for something that runs in exponential time, for a small input like 8, we have 2 to the power 8 being 256. For an input like 512, we have a very large number, right? It's 1 with 154 zeros after it. Okay, and it's even a little larger than that because 1.34 multiplied by 1 with 154 zeros after it. And that's a very, very big number. And so if we have 2 methods, one that executes in, let's say, linear time over here, and one that executes in exponential time, we would obviously choose the one that executes in linear time because the exponential time one, while it may work all right for small inputs, is completely impractical for large inputs. And that's why we're actually, even when we simply discussed exponential functions, we already said that if you have a method that runs in exponential time, it's actually impractical. So we'd want to find some way to express it that allows us to be able to execute it in polynomial time, if possible. All right, so now we want to consider 2 different sorting algorithms, right? Both of which you should be familiar with. Insertion sort, actually we already discussed this one. We said this is the one where you have an array, if we're doing this within a fixed array, you move from the left to the right of it, each time making sure that the left part is sorted. So when we start with the first element, it's sorted because it's a single element. Once the second element, we check, is it less than the first element? If it is, then we swap those 2. Then the third one, each time checking that we are keeping it sorted. All right? You could actually derive how we get to this. If there are n elements, 1, 2, 3, up to n, for this one, we do nothing. For this one, we compare it to everything to the left of it. So we do a single comparison. For the third element, we compare it to up to 2 elements to put it in the correct place. So up to 2 comparisons. Then the next one, we do up to 3 comparisons, 4 comparisons, all the way up to n minus 1 comparisons. So if we now sum up all these numbers, 1 plus 2 plus 3 plus all the way up to plus n minus 1, what do we get? What is the answer to that? All right, so the story goes, which I'm sure isn't true, that Isaac Newton, when he was a kid, was in school and was being rowdy in class or something, and his teacher put him in a corner and said, okay, add up all the numbers from 1 to 100. And a few minutes later, he was like, okay, here's the answer. And the teacher was like, there's no way that you could add all the numbers. Okay, one says Gauss. And so there's no way you can add the numbers from 1 to 100 in that length of time. And what he figured out was that if I put this sequence, if I sum the sequence itself in reverse order, I end up with the same value for each term. And then if I put it in reverse order, n minus 1, n minus 2, plus n minus 3, plus all the way up to 1, I see that if I add what's above and below, right, each time I end up with exactly n. There are n of these terms, so it's n multiplied by n, but I've added the sum to itself, so I divide by 2 to get the original value. And that's simply n squared over 2. All right, thank you for that paste. So this is exactly what you end up with, n squared over 2, and that's exactly what we have there for insertion sort. And we understand why, because each time we are considering the current element and comparing to everything to the left of it. All right, then what about merge sort? For merge sort, would be halving our array each time. So it would be some recursive function that each time looks at the portion array that it's been given. If the array is of a single value, then it simply returns that particular value. Otherwise, it halves it, and only in the base case does it return that value. Then, when they're merged back together, it sees, well, which one is larger than the other and puts that in the correct order. Right. That comparison to put in the correct order takes linear time. The splitting takes logarithmic time, because again, it's how many times can we divide it by 2. And so we end up with this n log n. Right, so we have one that runs in quadratic time and one that runs in n log n time. And now we want to consider, well, which one is better? If we were to, again, here we have on the left, look at the number of time, the number of operations based on the size of the input. So on our x-axis there, we have number of elements. And on our y-axis there, we have the runtime. We see that although our quadratic one, our insertion sort, is a little quicker for small number of values, going up to up to 100, as soon as we end up with more than that, then its growth rate rapidly increases compared to the merge sort, and so we should actually take merge sort and not insertion sort, right? And in fact, what happens when we have many items? We already have the answer to that. If we sort 1 million items, insertion sort would take roughly 70 hours, while merge sort would take roughly 40 seconds. And that's for the same number of inputs. That's a huge difference, right? So that's on a slow machine. If we have a machine that's much faster, it would take 40 minutes for our insertion sorts, but half a second for our merge sort. And so just think, which would you rather use? Would you rather have a method that takes 40 minutes to do the sorting part, or one that takes half a second to sort a given array, right? Certainly your answer should be, I would want the one that takes half a second, because that is much quicker. Right, so when we're doing this analysis, we're assuming that we have this ideal machine that has this unbounded amount of memory, and so that's why it's okay for us to do this. Could you please see a quick demonstration showing visually how a merge sort works? All right, let's say we have an array. So it has some values within this. We won't get to those values. So it'll be a recursive function. Our base case would be if your array has a single value, then you return that array, it's already sorted, and you simply put it and the other one that was returned to you in the correct order. Right? So you compare it, you have two sorted ones, and you should compare them to put those values in the correct order. However, as long as you don't have one that's a single element, you will split it in half. So we'll split this one in half, split that in half. Okay, that's the other half. Because we call the method, again, it splits it in half, splits it in half. So the splitting part doesn't actually do anything, simply keep splitting them in half. Then when you have a single one, it returns each one of these single ones, and I move to the right here, and make sure, let's call this one x and that one y. Our method then compares x and y, sees which is smaller, puts that one first, let's say y was smaller, and merges that with x on the right. So we now have a sorted one. Then, let's say this one had split into A and B. The same thing was done with A and B, so it should now be in the correct order. Let's say that order was A and B. As those are returned to this method that had split them, it then checks, okay, which is the smaller one, X or A? Sorry, Y or A, because these are both in the correct order. So Y will be smaller than X, A will be smaller than B. Which one is smaller, Y or A? Whichever is smaller, it puts that one first. Better. Okay, so it puts A first. Then it compares. So then it increments this one to the right, and it compares. Well, which one is smaller? Y or B? Perhaps this one is smaller than X and B. Perhaps B was smaller than X. So because we're doing this comparison each time, we're going to do this over the entire array in linear time, as in everything's going to be compared to one another. Not to one another. They're going to be compared element-wise, which gives us that n factor, and the splitting gives us that log n factor. All right. So something like that. It splits them, and then it merges them together in the correct order. All right. I'm sure Wikipedia has a nice graphic which shows that being done. So now we want to move to bigger notation. Now that we realize that we're able to express these functions, we're able to express the runtime of these functions by counting primitive operations. We can't say the time taken is that number of primitive operations. It's rather some multiple of that number of operations, right? We understand that based on the time that it takes for each primitive operation, it's bounded between the number of operations multiplied by the time it takes the quickest operation and the time that it takes for the fastest operation. So we have some idea of the growth rate. So now we want to use this nice notation that allows us to be able to discuss the growth rate of a function by considering its most important aspects. We will see that in the end, that is the higher order term, the highest order term, and that constant multiples and constant values don't matter, but we want to build up to that. And so we want to introduce this notation, which I'm sure you've used before, but we want to discuss exactly what it is and how we will apply that. So big O notation says that given two functions, f of n and g of n, we say that f of n is big O g of n if f of n is bounded from above by g of n. What this means is that I can find a positive constant c, which is greater than 0, and integer constant n0, which is greater than or equal to 1, such that for these values that I have found, this c and this n0, f of n will always be less than or equal to c multiplied by g of n for all values n greater than n0. So what does that actually mean? It means that I can have my f, I have my g. Yes, for different values of x, we may find that my f of n perhaps was greater than g of n initially, but I can find some point here, right, n of 0, for which f of n multiplied, oh, now I'm looking at the wrong one. This should have been my g of n. Sorry. This was my, no, that was my g of n. Sorry, yes. So I can find some value, some input n0, such that for all inputs greater than n0, this g of n will always be above my f of n, right? And it can be any scaled up version of that g of n. So I may have to use some c that's a positive number, that a positive constant that will make g of n always greater than f of n. So f of n is bounded from above. It will never exceed g of n. Even if they may be equal at some point, f of n will never be greater than g of n. Right. Why is this useful? Well, if g of n is simpler for me to consider than f of n, then I know that the behavior of g of n, right? Let's say that g of n is expressing the time taken to do something, some amount of time, that f of n will always be less than or equal to that. Right. So this can also be said that f of n is big O of g of n, or f of n is ordered g of n. There are different ways of expressing this, but the notation we'll use is this one right here, that f of n is big O g n. Right, so what we want to prove now is the function 8n minus 2 big O of n? We said that it's a linear function, so it should be able to bound it from above by some other linear function, as in it will never be, we can find a linear function, some constant multiple of n, such that for values n greater than n0, it will always be, 8n minus 2 will always be less than that function. All right, let's erase this so we can consider just that. So we would like to find some c and some n0 such that c multiplied by n is always greater or equal to 8n minus 2 for n greater or equal to n0, right? So for us to be able to say that 8n minus 2 is big O n, we have to find some constant multiple c and some n0 such that 8n minus 2 is always less than c of n. We could solve for n, but a really easy way to do this is simply take all our coefficients and add those up and use that as our c. So what am I saying here? I have the coefficient here 8 multiplied by n. I have here the constant 2, which is simply then 2 multiplied by n to the power 0. Okay, it is, you can think of it as a coefficient. So if I take 10, their sum, to be my constant multiple c, then is 10n always greater than or equal to 8n minus 2? And let me take my n0 to be 1. For n greater than or equal to 1. Is this true or not? Well, if I split this 10n to 8n plus 2n, then what do I see? 8n is always greater than or equal to 8n. Surely they're equal. And is 2n greater than or equal to negative 2? Well, for positive n's, it is greater than or equal to negative 2. And because we've taken our n0 to be 1, our values of n will always be greater than or equal to 1. So for example, if n was 1, I'd end up with positive 2 here, which is greater than negative 2. If n was equal to 2, I end up with 4, which is greater than negative 2. In fact, for any value of n greater than or equal to 1, my 2n is always greater than negative 2. So this sum, 8n plus 2n, is always greater than or equal to 8n minus 2. And so for c equal to 10 and n0 equal to 1, it does hold that g of n is always less than or equal to that 10n. So I can say that this value that we had here, this function that we had there, is big O n. Right? So to prove it, all you have to do is find a c and an n0 such that this holds true. Right. And oftentimes it is simple as looking at the highest order element or the highest order term, look at all the coefficients and those coefficients, and that'll give you the answer that you're looking for. All right, but we'll look at a couple more examples. Here we have 2n plus 10. Is it, we want to show that it is order n, so we want to find a c and an n0 such that Cn is always greater than or equal to 10 to 2n plus 10. So what's done here is done in the text. We solve for n, then we choose an n and a c such that this holds true. But as I said, it's usually simpler to consider 2n plus 10. We want to show that it is always less than or equal to Cn. We can choose a c that is greater than or equal to the sum of the coefficients. So here I choose a c of 12 or greater. And I can see that okay, what value of n would I have to choose for this to hold true? For any value of n 1 and greater, this will hold true because these first two terms will be equal to one another. And for n greater than or equal to 1, then 10n will be greater than or equal to 10. For n equal to 1, they'll be equal. For n equal to 2, 20 will be greater than 10. For n equal to 3, 30 will be greater than 10. These are always positive numbers multiplied by 10, and so that will always be greater than or equal to 10. So for C equal to 12 and NO equal to 1, then this will hold. Right? NO should be, yes, NO is mathematics 1, yes, equal to 1, then it will hold that 2n plus 10 will be less than or equal to Cn. All right, so this is one solution. This is another solution. As long as you can find a solution, it proves that 2n plus 10 is big O n. All right, questions before we continue? None? We're all on the same page? Okay, well, that's good. All right, if questions do come up, please just type them into chat and I'll address them. So we could do this for many other examples. Here, though, we find one that we can't prove. So example is the function n squared big O of n? And the assertion is that no, it's not big O of n. If we were to try and disprove this, can we find a c such that n squared will always be less than or equal to c of n? Think of the largest c that you can think of, right? Let's say a billion. Let's say 1 billion. So I say, if I take 10 to the power 9 as my c, then that will always be greater than or equal to n squared. For some values of n, this may be true, but as soon as I get to a value of n whose square is greater than it multiplied by 10 to the power 9, then I will exceed this. I can think of an example like that. Let's see. If I have 10 to the power 10, 10 to the power 10, then its square will be 10 to the power 20, while on this side, 10 to the power 10 multiplied by 10 to the power 9 is simply 10 to the power 19, right? I can't make this work. There's no way that I can make this true. I can never choose a C so large that will keep the one function less than the other. A linear function will always at some point for some value of n be exceeded by a quadratic function. And it's because we can never find a C that's greater than this n, which grows. Right. So because it cannot be satisfied, n squared is not a linear function. It's not bounded from above by some linear function. It will always exceed that at some point. And there's a question for the multiplication case. How would you choose C? What do you mean by multiplication case? Do we mean where instead of having like separate terms like we had, whatever that was, 8n minus 10, so you are instead having what, 8n multiplied by 10? Well, that would be even easier because we simply have 80n, and so we'd choose a C that's just bigger than 80, 81. Then you know that 81 multiplied by n is greater than 80, so it holds true. If we're instead multiplying by other terms that are dependent on n, well then you'd have to find some function that's always greater than that, and I wouldn't be able to find any coefficient here that makes that multiplied by n greater than or equal to some multiple of n squared, and so this would not hold true. Right, and that's what we saw here. Then, is 7n minus 2 on? Yes, we could easily find a coefficient C, a constant coefficient C, such that C multiplied by n is greater than 7n minus 2. A very easy one to choose would be 7, right? Because if I have 7n on one side and 7n minus 2 on the other side, this will always be greater than or equal to that, or positive n's. So as long as I take my n0 to be 1 or anything greater than that, I know that 7n will be greater than something less than 7n. 7n minus 2 will always be less than or equal to 7n. And so I very simply find a C and n0 that work, and so this is true. All right, and then what if we do have a polynomial like this? Well, for these ones, we would simply, again, take the coefficients, 3, 25, add those together. That gives me 28. And I'll see that for 28 as my C, and let's take my NO0 to be 1 again, that this will hold true. That 3n cubed plus 20n squared plus 5, if I were to split up this 28 into 3n cubed plus 20n cubed plus 5n cubed, then each of these terms on my right is greater than or equal to each of the terms on my left. This is equal to that, 3n cubed is equal to n cubed. Well, for positive values of n greater than or equal to 1, 20n cubed is indeed greater than 20n squared, and my 5n cubed is greater than 5. So I've found a C equal to 28 and an n0 equal to 1, such that this holds. It's over here, and so we've proved that it is indeed order n cubed. Right. If these things come up in the test, please tell us an example of how these might be asked. Exactly like this. Okay, prove that 3n cubed plus 20n squared plus 5n is big O n cubed. So what do you have to do to prove that? You have to find a C and an n0 such that C multiplied by n cubed will always be greater than or equal to the function that you're given. That's our g of n, for values of n greater than or equal to n0. Find those two numbers, that proves it. All right. Then for our second example here, 3 log n plus 5. Again, we choose a c that's simply the sum of our coefficients, 8, and we find that 8 log n is greater than or equal to 3 log n plus 5. Why? Because as long as we have, well, what does our log function look like? Okay, and this one's important because for this one, we can't simply take n equal to 1. For the other ones, we're simply multiplying n by some number, right? But for here, we're actually taking the log of n and multiplying that by 8, and log of n isn't always greater than 1. For inputs, remember that our log base is 2. For inputs less than 2, log of that number is less than 1. So for example, log base 2 of 1, what's that equal to? Two ways to consider it. How many times can I divide 1 by 2 before I get a number smaller than 1? Or to what power do I have to raise 2 to get 1? 0, correct. All right, so if I was to split this to 3 log n, do that. 3 log n, scratch that out. 3 log n plus 5 log n. For n equal to 1, both of these would be equal to 0, and that would be less than 0 plus 5 on my left. Right? So this is not true for NO equal to, so for n equal to 1, so I have to choose my NO to be greater than my base. That's why we have here NO2. Right? NO equals 2. Because my base is 2, and for values less than 2, the log base 2 of that number will be less than 1. Right. So the reason that we can simplify this and simply look at, okay, we have one question. Could we do an example on whether, whether n log n is big O n? Okay. The question is n log n Can we prove this? Well, let's see. Can we find a C such that C of n will be greater than or equal to n log n? So if we divide by n on each side, because we are taking positive values, we end up with solving for C. Can we find a C that will always be greater than log n? Can you? Remember our logarithmic function, its growth rate, does it something like that? Its growth rate does peter off. However, it never stops increasing. Yes, it increases at a very slow rate, but doesn't stop increasing. And so we can't find a C, a constant, that will always be greater than log n. Right? So this isn't the case here. N log n is not big O n, as in this function n log n is not bounded from above by some linear function. We can't find a C such that n log n will always be less than Cn. All right. So why we will consider the simplest linear or quadratic or cubic function rather than our particular function is that the growth rate is not affected by constant multipliers or lower order terms. So we have an example here. 10 to the power 2n plus 10 to the power 5, that's a linear function. Whereas 10 to the power 5 n squared plus 10 to the power 8n is a quadratic function. If we look at how, these aren't labeled well, which is great, but if we look at, here, let's go, this one, this hatched one here is this function, let me call it f of n. f of n, that's this one over here, f of n. If we compare that f of n to a lesser quadratic function, this one should be a quadratic function over here, then even though they may start at different places, as in they have different constants, or they have different multipliers, so different coefficients, we see that their growth rate, the rate at which they increase, is the same. Right? The same with our linear functions. Even though the perhaps intercepts are different, even though their gradients are different, the rate at which they increase as a function of their inputs is the same. Right? They'll be bounded by the same types of functions. They will grow in the same way. Right. And that's why it's enough for us to figure out, well, what are these algorithms? What is their behavior? What is their growth rate like? Is this a linear function? Is it a quadratic function? Is it a cubic function? Even though perhaps the one that we're comparing it to is a linear or logarithmic function that has a large number of constant operations that have to be done, or they have different multipliers, as long as their growth rates are described by the same functions, they will grow in the same way. Our constant factors and our lower order terms don't actually change that behavior. Right. And here's a better example. Here we have different linear functions. Our hatched line is now 3n. Our blue one there is 2n plus 10. And the solid red one is n. All of these are linear functions, right? They do have different intercepts based on whether they have a constant term or not, and their different coefficients give them initially different behavior. But as we look to this section, the rate at which they're growing, right, for larger and larger inputs grows in the same way. Right. And that's why we can say that all of these are linear functions. All of these are bounded from above by some linear function. We can always find a c, such as c multiplied by n will be greater than any of these functions. Right? We're shown here how this is true for 2n plus 10. For 3n, it's even simpler. I can just choose 4. For n, I can simply choose 2. And so I can always find a c and an n0 such that all three of these functions are bounded from above by a linear function. Right, then we have the example of comparing a cubic function to a linear function. Why is it that we can't say that n squared is on? We can never find a linear function that are always bounded from above. Here we have linear functions with greater and greater coefficients. So the one at the bottom there is n, then we have 10n and 100n. Although the ones with the larger coefficients will be greater than n squared for more inputs, at some point our cubic function will be larger than those linear functions. There's no linear function that we can find that will always be greater than our quadratic function. And so this is why, even if our linear function has perhaps a lot more, a larger constant term in its expression of the number of operations, that means perhaps there's a large number of operations that have to be executed every single time, regardless of our input. And perhaps even for those inputs, we are traversing them a certain number of times. So we have really large coefficients like this 100. Our function, there's a cubic function, like our insertion sort, will for larger inputs always take a longer time than the other ones, even though those linear ones may have a large number of constant operations or these large multipliers that we have like 100. And that's why we can boil it down to simply, is it linear, is it quadratic, is it exponential, and know that the linear one will work better for larger inputs, regardless of those constant multipliers and constant terms. Right, and so this asymptotic analysis, which allows us to determine runtime in big O notation, allows us to find the worst number of primitive operations that will be executed and express that in big O notation. Right. We have a couple more slides to do. We'll look at, well, what type of, how we'll express that big O notation in the simplest form. But are there any questions here with the theory that we've covered before we simply look at how we'll express these? Do you understand why it's enough for us to count our number of primitive operations, express those as a function of the inputs, and that allows us to compare different algorithms without implementing these algorithms? All right, good. So that means we're on the same page. So, all right, we'll leave it there. We'll do the next couple of slides tomorrow. And actually, since we only have about 8 slides left, that will leave us sufficient time to get started on the next lecture, which is good because we still have about 5 lectures to cover before the end of this term. The question was last time, and again, what is the title going to be on? It is going to be a W-linked list. We haven't actually gotten to a new ADT yet, so definitely be on that we covered last week. But it shouldn't be too hard compared to the other ones. Okay. We go back to primitive count where there's a while loop. The first return I saw 1, and when you explained, you said that n because the loop was inside. All right, certainly we can go back and right, I believe that was this one. So the question was, all right, I'll get to that next question. Question was, the first return I saw 1, and I explained that we return n because, okay, I see. So you're saying that this return can only ever be executed. Oh, okay, no, I see. All right, so you're asking why is it that we have a 1 here, even though I said it will be n. All right, so that was an error. It is a single primitive operation. It is within my loop. However, unlike our conditionals, which our conditional statements like this if1, which in the worst case can be executed up to the number of times that the loop is executed, a return statement is special in that as soon as I execute that, I'll actually exit the method. So even though that is within my loop, that should be 1 and not 1 multiplied by big N, which turned out to be log n. All right, so thank you for that. That is a correction. The return statement can only be executed once, regardless of where it is within our code. And so that'll be an exception to our rule of multiplying all our primitive operations within that loop by the number of times that loop is executed. All right, and then someone asked, can you please explain a bit more about the mini project? All right, you should all know that the mini project proposal form is up, and you have to fill out that form to simply explain what it is that you want to do for your mini project. I assume that you have gone and looked at the 3 videos that Prof. Nahal put up regarding blockchain, and so you'll understand that a blockchain allows us to create a tamper-proof history of, let's say in the general sense, transactions that have occurred. Right? It doesn't matter if we're talking about financial transactions or writing things to a database, that is a type of transaction, or anything. We understand that we're able to create a tamper-proof sequence of transactions that it will be very difficult for someone to go back and change any one, because as soon as you change one, you have to change all the subsequent ones, because each block within that chain stores its own hash and the hash of the block before it. So if I change the block before it, that changes its hash, which changes the hash of the new block, because that block considered the hash of the previous one in its data, and that data is then hashed to get the hash of that particular node. So each of these blocks considers the block before it, which means that if I change one block, I have to change all the ones after it. So just the blockchain itself gives us a tamper-proof or tamper-resistant, it's not completely proof, it's a tamper-resistant sequence of transactions. However, how do we agree on what a new transaction, on which new transactions should be accepted. So the chain itself is not to make sure there aren't changes that are done. However, to be able to make sure that we're always adding legitimate transactions, we use this network of nodes, of machines that each store this blockchain. And by communicating with the other nodes on that network, we can agree, reach by consensus, which are legitimate transactions to add to our blockchain. And so you're going to represent this network by a graph. Okay, assume that each of your nodes within your graph would store its own version of that blockchain. And when a new transaction is done, then all of these nodes should speak to one another to reach some consensus on, well, of all the nodes within this blockchain, what does the majority agree is a legitimate transaction? And that should then be added to that. So two aspects of it. They're actually keeping this chain and adding new transactions to it, but also communicating within this network of nodes to agree on what's the next legitimate transaction to add to that. All right, so that adds this fault tolerance of not being able to change things that happened in the past, but also not being able to change it and update the new ones and take that as the new blockchain that has some illegitimate transactions within that, because each new one has to be agreed by consensus within that network. All right. And then a question, does our ledger have to be distributed? Yes, because if it isn't, then someone could recreate it, as in could make a change and then create the subsequent ones by itself. Because, well, yes, some ones like Bitcoin have added this work that has to be done that makes it not doable in a realistic amount of time to completely recreate that ledger. However, not all of them have that. And so to make sure that someone hasn't made any changes, we always use that communication, that idea that everybody has copies of it, and we compare our copies to that of the others to agree on which is the legitimate version of it. So we need to implement our own consensus. Yes, you will. That will be the communication that you have over this network. So how do we traverse the network in such a way that we can send messages between the neighbors that we have to find out information about their neighbors and the neighbors that they have? And so we know on this network, everybody's agreeing that this is the correct new transaction to store. And I can always check my blockchain against my neighbors to see that it is still the correct version. No one has changed it. We have to create our own blockchain. Yes, you have to create your own one. You're only given the node structure, the graph, but you have to create your own blockchain. If I add half an hour transactions to the chain, tampering, will the chain accept the changes? Well, this is the thing. You could do that to your local one, but then when you compare yours to all the others, there's no way that you could make your new tampered one the new official one without changing not just yours, but at least half of the other ones as well. So the bigger your network, the less feasible it is that you could change yours and all those others to be able to put this now tampered chain and make that the official. Okay, one of the questions in the Google Sheet asks how the blockchain state will be distributed. Can examples distribution be amongst the nodes? Yes, that would exactly be it. How are you going to share this information across the nodes of your graph? There has to be some traversal to do that that is an efficient way to send information between the nodes of that graph. Right, and I believe we still have a couple of days to do this. We have until the 4th. So please, if you haven't started thinking of this, please do right away and make sure that you get that in on time. The idea is that we will then give you some feedback. So we'll look at the proposals, and if they aren't, if you're not on the right track, we'll then let you know that these were not accepted. And usually, Prof. and Howell give some feedback on that, a short video that basically explains where people were having difficulty. So those of you who need to rethink your ideas will be able to do that. All right, but of course, if you get the feedback that it's fine, then you can go ahead and get started on your project. All right, so a bit of the time.